The result I'm going to present is from 2022. I just figured it's kind of probably be of most broad interest to the people here. And it's joined with Peter Smillie, who's a junior professor in Leipzig. And so just before we get into it, the general principle that's guiding this talk and every job application and grant proposal that I write is that to study a space, one should examine maps into and out of that space. And then from the standpoint of geometric analysis, one will have a better chance of understanding something if you look at maps that solve partial differential equations or extremal problems. And in today's talk, I'm going to be focusing on maps into spaces. And just, the most basic example would be geodesics. And in this talk, my focus is going to be on harmonic maps and minimal immersions. So I'm going to tell you some general things about harmonic maps and minimal immersions, but centering the discussion around Labourie's conjecture, which was a problem in the field. Yeah, cool. So the space we're interested in today, I'll denote it Xn. It's an example of a symmetric space, and my model for this is matrices A in SL and R that are symmetric and positive definite. And this space comes with a Riemannian metric that I will denote by nu. The formulas aren't so important to define it. You want to define on each tangent space. This is some space of matrices. The tangent space at every point is some space of matrices. And so it's given, evaluated on 2 points xy by n over 2 times this trace form. So we're not going to bother with the formula. But what I want to point out is that SL and R acts on this manifold by isometries. For n equals 2, this space identifies with the upper half space. So this to me is complex numbers with positive imaginary part. And nu is a hyperbolic metric of some constant negative curvature. So this is a space that hopefully we're familiar with. And the action by isometry is just the ordinary action by Mobius transformations. And then for all n at least 2, this is just some space that has non-positive sectional curvature. And the distinguishing feature for every n, so xn has copies of Rn minus 1. And they're called flats. So just in this picture for H2, which I can always draw as a disk, the flat is a geodesic, which is a copy of R. So why this space? Well, as we'll see, it has some very nice structure associated with it. And it's a general model for a non-positively curved manifold that's complete. So the hyperbolic space could be your first example of something you study in non-positive curvature, but this actually has flat subspaces, so one can learn a lot by studying it specifically. And as well, this is one of the most basic examples of a symmetric space of non-compact type. I won't define symmetric spaces, but typically if you say things about this space, you can say them about the more general symmetric spaces. And also, just comment that 90% of this talk goes through by replacing SL and R with some semi-simple Lie group of non-compact type and Xn by the associated symmetric space. Okay, so I said we're interested in studying something about xn. So x is going to be a closed surface, to me always oriented, of genus at least 2. S tilde is the universal cover, and I'm having the pi1 act on S tilde by deck transformations. So the quotient is S. And the interest of myself and other people is in homomorphisms or representations of the pi1 into SLNR. So this is what we'll be studying. And to study such actions, we typically consider row equivariant maps F from the universal cover to Xn. And so row equivariant, color. Row equivariant means that for all gamma in the pi1, F composed of gamma is row of gamma composed of F. So while the action might be hard to get your hands on, it's just some matrices. If you can represent it by some nice map inside this space, maybe you can get your hands on that and learn something about it. And the example, to keep ourselves grounded, is if rho is discrete and faithful. So discrete means that the image inside of SLNR is discrete topologically. And faithful means the action is faithful, or in other words, the homomorphism is injective. And this implies that Xn mod rho is a manifold. And so any map from S to Xn mod rho lifts to an equivariant map. So if you find thinking about a group action annoying, you can always pretend for yourself that what I mean is just a map to a quotient. But this is a generalization where the action can be very nasty and the quotient might be like totally non-Hausdorff. And just more generally, this doesn't have much to do with these spaces Xn and S. Any map between manifolds lifts to an equivariant map between universal covers. So this is just the specific examples I'm working with. Okay, and great. And so I said we were interested in maps that solve some sort of PDE or extremal problem. So the first type of map I'll define is a minimal map. So F is minimal if it's a critical point for the area. And so the area is this function obtained by integrating some 2 form over S. So just to unpack this is the determinant of the pullback metric that's a 2 form on the universal cover, but then because you're acting by isometries, this descends to the surface S and can be integrated. That's the formalism, but the way to think about this is if your map is discrete and faithful, this area is on the nodes the area of the image of this inside here. And then if you're thinking equivariantly, you could pick a fundamental domain and take the area of the image. And just what I mean by critical point, to keep ourselves very square, I mean that for all paths of maps, we go into FT that are all row equivariant with the same representation. F of 0 is equal to F. The first derivative of area at time 0 is 0. So critical in this sense. Of course, if you're a globally area minimizing surface, then you're a critical point. Okay. So next, let's discuss the actions that we will be interested in. And these are called Hitchin representations. So for n equals 2, if I have a representation that's discrete and faithful, this occurs if and only if the quotient of H2, which is x2 mod sigma, is a hyperbolic surface of, the same genus. And more or less up to equivalence, some form of equivalence, every hyperbolic surface arises in this fashion. So the picture that probably people are familiar with is I have some fundamental domains inside H2, and then I quotient by reaction and get my surface. Okay. I'll leave it on. Okay, so that's fine. And then for all n at least 2, there is an irreducible representation from SL2 into SLNR, which is more or less unique up with some choices in which you can write down explicitly. So to produce a nice action on this space Xn, you could consider iota composed with sigma. And now, this is a nice action. So this one, sigma is discrete and faithful, so that implies the same thing. And so the quotient of Xn by iota composed with sigma is some manifold. And living inside of it, you have this totally geodesic and isometrically embedded surface, which is just H2 mod sigma. So this is some nice representation to SLNR that is completely encoded by a surface inside the quotient, so from which you can read off all information. This really isn't the most interesting definition, because we took something we're supposed to understand, which is hyperbolic surfaces, and put them somewhere else. So that brings us to Hitchin representations. So I call rho to SLNR Hitchin if you can find a path of representations, all to SLNR, starting at your Fuchsian point and terminating at rho. So it's just something connected to the Fuchsian point. If you want, you could say that the space of representations to SLNR has some number of components, and it's anything in the same component as the Fuchsian representation. Great. Now, there's no reason a priori why that should be interesting. I took something we considered interesting and I deformed it. And the theory around Hitchin representations has been developing for the past 30-something years. And I totally don't have the time to tell you why people find them interesting, so I'll just tell you two theorems, both due to Francois Labourie, that were proved at different times. So let rho be Hitchin. Then 1, rho is discrete and faithful. So in particular, the quotient x on mod rho is a manifold, maybe a little bit more wiggly than the one I drew over there. This is kind of surprising. There's no reason why. You know, if I deform something, a representation that's nice, maybe it should stay kind of nice. That sounds reasonable. But there's no reason that being discrete and faithful should be a closed property. That's quite surprising. Especially, I'll just comment that if you replace SLNR with SLNC, then this is just completely untrue. So that's something sort of unique. And the second thing he proved is that there exists a rho equivariant area minimizing immersion from S tilde to Xn. So in particular, inside the surface, there is some nice looking minimal surface from which you can hopefully read off a lot of information. And you know, up to this point, people have used these minimal surfaces to prove a bunch of cool things. Great. Yeah, so just before moving on, I wanted to, did I pause to say some words? I was looking at the conference poster, and it says bringing together people from geometric group theory, metric analysis, some other fields, and one of those fields is called higher Teichmüller theory, and I think I'm the only one not at Bonn who's working in that field. So I thought it necessary to say a couple words that are just for context. So if you look at the space of discrete and faithful representations from the pi1s to SL2R, and I'm actually lying a small amount here. If you look at a component of this space, mod conjugation, this is called the Teichmüller space. This is equivalently the space of hyperbolic metrics on your surface up to some form of equivalence. And you know, the theory's been well developed over the past 100-something years, and I'd say a foundational object in low-dimensional geometry and topology. And the kids these days are studying the space of Hitchin representations from pi1s going to SLNR, modulo conjugation. And this is called a higher Teichmüller space. So you can nail down precise definitions, but loosely speaking, is some space of representations that's typically open and closed that communicates some meaningful geometry. And so some of these questions I'm discussing fall into the realm of higher Teichmüller theory. Okay. Yeah. Do I wet this to? Okay, and so the main problem I'll discuss today is called Labourie's conjecture. was made in 2004, which is that if rho is Hitchin, then there exists a unique rho invariant minimal surface. So he proved a year later that there always exists a invariant area minimizing surface, so the entire question is about the uniqueness. And my dates might be like slightly off, but I think in 06, same guy, he proved it's true for n is equal to 3. Yeah. To me, okay, why work on this problem? I study harmonic maps and minimal surfaces for some reason, and that's interesting to me. And these minimal surfaces have been used to prove a lot of wonderful things about Hitch representations. So I thought that was a good enough question to care about. Is it unique? And studying that question will help us understand these surfaces. But it became quite popular as well for other reasons. There were some rather strong motivations coming from this higher Teichmüller theory. And I won't linger, I won't explain them, but there's a group called the mapping class group, which is also kind of foundational in at least the topology of surfaces. And understanding minimal surfaces and how many there are can help one understand how the mapping class group acts on this space of Hitchin representations. There's actually a survey article on my webpage that explains it all pretty carefully, or I can tell after kind of what these motivations were. I also don't want to hype the motivation too much because the main theorem I'm presenting is as follows. So for all n at least 2022, for all n at least 4, and genus at least 3, there exists rho Hitchin with at least 2 minimal surfaces. So in particular, for all n at least 4, this conjecture is false. Before Hausdorff questions, I'll say something more precisely. Really, the first thing we showed was that under the same assumptions, there exists rho with what's called an unstable minimal surface. So what this means is you have some path of maps, t going to ft, all equivariant for the same representation, and starting at your surface, such that the second derivative of area at time 0 is negative. So minimal means you're a critical point for the area, and unstable means your second derivative is negative along some path. And so why does this prove the theorem? Well, Labourie proved that since this is Hitchin, you can always find an area minimizer. Right? This implies rho admits an area minimizer. And this property, of course, means you can't minimize area. And so that's going to be, so this is clearly not unstable, or the correct term for that would be stable. Cool, so this is, I'm going to, for most of the rest of the talk, I'm going to go through the proof of this result, constructing an unstable minimal surface. Are there any questions?
Yes, the existence result for the minimal one, this is the proof of Labourie.
Yes. His proof is a little complicated, but I actually have a separate proof as well in this survey article that I wrote, and it's kind of there's a very classical proof of Shane Yao for existence of minimal surfaces in negatively curved manifolds, and essentially Labourie shows that these Hitch representations have enough properties for that proof to push through. So the existence isn't terribly difficult, actually. So yes.
After your result, one can try to bootstrap whether to refine the conjecture of Labourie was saying that there exists a unique row invariant area minimizing surface. Do you think that could?
Yeah, so we also proved you have non-uniqueness of area minimizers.
Okay.
Yeah,
okay.
I was just,
That is
I was too lazy to write that down.
okay. Okay.
Yeah, I actually usually pause so someone asks.
For SL3 it's true and for SL4 it's false, and what
Yes.
happens for other symmetric?
I wrote for all n at least 4, g at least 3. Right, the proper statement is that if g is a split real, let's say simple, I can do things for no, g is a split real E group, so that means a product of split real simple E groups. If the rank is 2, you have uniqueness, and then we proved if it's at least 3, you always have non-uniqueness, is the more general statement. And when I, actually maybe very soon, I'll say what rank is in words and you'll see why. Yeah. Okay, cool. I think that's what I wanted to state. Okay, so the rest of the talk I'm going to tell you a number of things about harmonic maps and minimal surfaces that will kind of explain how we do this. So here's the underlying picture. So first, we want to recall that Xn has copies of Rn minus 1 called flats. Yeah, so actually right now I can address your question. This is a symmetric space of rank n minus 1. The rank is the dimension of a maximal flat subspace. So it's having at least 3-dimensional flats in your symmetric space that is what we use. Okay, so let's note now H going to Xn be an equivariant minimal immersion. Okay, 2 facts that are kind of easy. So first, it can be proved from the right definition of minimality more or less immediately that your Gauss curvature is always of the image surface is always non-positive. The other fact take note of is Gauss-Bonnet. And I use this to say that the average Gauss curvature, well, this is 2 pi times the Euler characteristic over the area. And this is like minus the area to the minus 1 when the area is large. Okay, so I have this fact, the Gauss curvature, non-positive, and when your area is large, it, is like minus the area. So this implies the following, let's say heuristic, is that if the area is large, this implies that your image surface H of S tilde mostly clings to flats. So if your area is large, then on average your Gauss curvature should be something very close to 0. So here I draw like a flat. If I take a point, it could be close to this flat, and it should be hanging out very close to the flat. The word mostly has done a lot of heavy lifting here, because Gauss-Bonnet prescribes some definite amount of Gauss curvature. But this integral is like an L1 norm. So what you might expect is that there are small regions on which the Gauss curvature concentrates and looks extremely negative. Some sort of Pringle that I can't draw. But away from those regions, those small regions, it should be, sort of close to flat subspaces. So there's some regions on which curvature concentrates, and I don't understand it. But away from there, it's close to flats. And when you pass through, it could be close to different flat subspaces. There's nothing ruling that in. But that implies the following cool thing, which is that H should at least resemble an equivariant minimal surface in Rn minus 1. Right? So if it's minimal, it means, one way of saying it solves some equation, and it's close to a flat, well then it should probably look like a minimal surface inside the flat. And the flat is a Euclidean space, so those we kind of understand. So that's my heuristic. And now if we back up, so for n equals 2, if I draw a two-dimensional plane, a local patch of this just looks like that, right? And so H should minimize the area. Oh, sorry, n equals 3, because then it looks like a minimal surface inside R2. And so I don't see any way to deform this without increasing the area. So there's no problem when n is 3. But then for n at least 4, H could look like an unstable minimal surface in Rn minus 1. And when I say minimal surface, I should also specify that it's equivariant, because H was equivariant to begin with, so there should be some equivariance property. Right, I said that there. Okay.
And one question.
Yes.
So the ambient space has a group action, but then does that action that action doesn't reduce to Rn minus 1, right? Because you have more bigger flats. So
yeah, so it doesn't. Yeah.
So what is equivariant in Rn minus 1?
Right. So what I mean is you could have, and I'm going to give you an example. You could have some homomorphism from pi 1 of s. I mean, one needs to figure out the right thing it means. But the right thing it will mean is you have a homomorphism from the pi 1 into the additive group of Rn plus 1, or Rn minus 1, sorry. An equivariant with respect to some action there. Let me draw an example of such a surface. There are examples. So one of the earliest examples I know is called the Schwartz P surface, which was discovered by Schwartz and his student in the 1880s. So this is a genus 3 surface inside the 3 torus, which to me is R mod z to the 3. And then you lift this to the universal cutter. And what is this surface? I take this minimal 6-fold sphere, which solves some plateau problem, and then I translate it by the Z3 lattice and duplicate it along that. And that is as much as I'm capable of drawing. But this is called the Schwartz P surface, and it's an example of unstable minimal surface in R3. And to see it's unstable, well, I won't give you details, but at every point you can draw the tangent space, and then a unit normal vector if you choose an orientation. And the small computation shows that if I call this map F over here, then the second variation of area, when you deform by this unit normal vector, this is negative. So, okay. So heuristic says that, we should look like some minimal surface in Rn minus 1 that's been bent in some ways at certain points, but, and if you don't follow the rest of the talk, that's totally cool. You can just think, well, this conjecture is true when n is 3 because I haven't given you a problem. I haven't given you a proof either. But when n is equal to 4, you could imagine that you have a minimal surface equivariant for a Hitch representation that looks like this one. Yeah. And so you can stop paying attention if you want. And now to turn this picture into a proof, there's a number of things you need to do. Firstly, how to create a minimal surface for a Hitchin representation that looks like this. And then the second step is how to use this picture to say that surface is also unstable. Yeah. And so that's kind of the technical part of the proof. And to do all that, I'm going to take a large tangent, but on things I find interesting. And this is going to be in non-abelian Hodge theory, is how we turn those pictures into proofs. So step away from minimal maps for a second. So now I'm going to let, I should pick a symbol. Sigma is now a Riemann surface. So this is just a, let's say, genus G. So this is, I've just put a complex structure on S. Chart for the complex plane with good transition maps. And I'm going to put on a conformal symmetric mu. So all that means to me is mu is like mu of z dz squared, where z is the local holomorphic coordinate. And so we say that h sigma tilde to xn is harmonic if it satisfies some differential equation. So this is some equation that when you can think of as the right analog of Laplace's equation, but for a map between manifolds. I hope some people have seen harmonic maps. Yeah, you can also, and why this is important for us is that harmonic plus conformal implies that you're minimal. And conformal just means your pullback metric is out of this form. And I'll also just point out this equation is conformally invariant, so I didn't really need to choose this mu. But anyway. So right, I'm going to now tell you some sort of very general things about harmonic maps of this space Xn, and then we'll specialize a bit in the minimal case and see how to prove the result. I made a mess. So to warm up on something called non-abelian Hodge theory, let's consider a more basic situation. I claim there's a correspondence between harmonic functions f from h2 to r, modulo translations, and holomorphic functions from h2 to c. So this is kind of our warm-up for thinking about whatever this non-abelian Hodge is. So harmonic, in this context, means del squared f over del z bar, del z is equal to 0. And holomorphic means del phi over del z bar is equal to 0. So C1 with Cauchy-Riemann equations. And the association is you take f to del f over del z. So that seems good. Z bar of this is 0. So, yeah. And then on the other side, you can take phi to this function f of z, where I fix a point v0, and then I integrate the real part of phi from that fixed base point to z. And the choice of base point here accounts for this translational ambiguity. So that we feel good about.
Translation by what?
Oh, just by a constant. Like if I just add like a plus c here.
Okay, so in coordinates.
Yeah, exactly. Yeah. Right. So now my claim is that there is some version of this, but for maps to this more complicated space Xn. Let's start over here. And so add some more words: equivariant, harmonic, onto Xn. And this should go to something. So what I want to do is try to take the z derivative. But the first question is, what is the z derivative of a map to this space? So the derivative formally is a one form valued in the pullback bundle of the tangent bundle. Your life is going to be easier if you trivialize the tangent bundle. All that being said, when you do that, it tells you to take the formula minus 1/2 h inverse del h over del z dz. It's a good formula to take for formal reasons. And what this thing is it's you can think of it as a matrix with the dz attached. So my space Xn is a space of matrices. So the derivative is a matrix, the inverse is a matrix. So this is some matrix with a dz. And I'm just going to call this thing an SLNC valued one form, say phi. SLNC is for the Lie algebra. And it's also got a fancy name, which is called a Higgs field. Okay, so if you take the derivative, you get this object. Yes?
So H is an element of the domain.
Yes, my bad. Thank you. H is the map. Yes. Thank you. So you take the derivative, in a sense you get a matrix with a dz attached. So here I have to be very informal. My claim is that this is in some sense holomorphic, this varying matrix. And so this is on the universal cover sigma tilde. And in what sense is it holomorphic? I have to give you more words, which is that phi determines what's called a Higgs bundle, say E phi 0 on sigma. And so this is a holomorphic vector bundle of rank n, and this is some phi 0, which is an endomorphism valued one form that is holomorphic. Okay, I don't assume people are so great with vector bundles, so just to explain this, I have sigma tilde, which I draw as a disk here, and over every point, I've got my phi, which you can imagine as a matrix with a dz, and ignoring the dz, it's acting on a Euclidean space, right? And so because this map is equivariant, you can patch these things together in such a way that it descends to a vector bundle over sigma. And then this phi gives you some endomorphism of that bundle with a one-form piece attached. And this is such a mouthful, but the way in which this is holomorphic is that this bundle, for some reason, inherits a complex structure with respect to which this is holomorphic. Okay. So that's what a Higgs bundle is. And doing all this, the point is that this is kind of a more tractable object than the harmonic map. So these objects are more kind of germane to what's called gauge theory or Yang-Mills theory. And there's a lot of interesting tools you can use to study it. So you can do plenty of analysis with a different toolbox. And yeah. And so I won't, of course, show you any of that toolbox, but that's kind of what goes into this sort of modern theory. And one version of the non-abelian Hodge correspondence says that if, well, let's say if this vector bundle with some n-valued form satisfies some properties, so some characteristic classes vanish and phi 0 has some properties, this implies it comes from a harmonic map. So the gist of it is, if I add some properties on the right-hand side over here, then I can reverse this arrow. And so, in particular, to create harmonic maps or minimal surfaces, you can cook up these more holomorphic objects and check some properties. And then, you can use constructions coming from, let's say, even algebraic geometry to construct these things. Yeah. Cool, that's quite a lot of content. So, are there any questions? Okay. So back to minimal surfaces. So now, if you have H xn harmonic, you can read off the minimality if and only if the trace of phi squared is equal to 0. So I said minimal is, or harmonic and conformal implies minimal. So you can read off the conformality property just from this Higgs field thing. And so, going back to the theorem, we want to construct these minimal surfaces with large area that resemble the Schwartz P surface. So to construct a large area surface, one considers a ray, R going to R phi, R greater than 0, with minimal maps HR. Then I'm lying a little bit, but generically, the area behaves like R squared. So if you scale up your holomorphic data, you get a large area surface. If you want to think of surfaces in Euclidean space, I mean, you can kind of see that here, and the scaling goes that way. But to prove such a result, you use this analysis of the Higgs bundles. Okay, so with that done, let's prove the theorem. So this is for, I'm going to do it for n equals 4 in genus 3, and kind of the very easiest way to do it. So we produce row Hitchin with unstable minimal surface. So to start off the construction, I take the Schwartz P surface inside R3.
Could you break the chalk, please?
Oh, so it's not louder. Yeah, okay, thank you. And then I isometrically identify R3 for reasons that will become clear. with diagonal matrices, let's say x1 down to x4, such that the sum of the coordinates is 0. Okay. So if I write f is equal to f1 down to f4, I set phi I to be the holomorphic one form associated with f. So now here's the black box, or the first black box, using a construction due to Hitchin with these Higgs bundles. We can find this array R going to R phi that that come from equivariant harmonic, or let's say minimal maps for Hitchin representations rho R, such that phi, or let's say phi is globally diagonalizable with eigenone forms phi 1 down to phi 4. Okay, that was a lot. So we can produce these Higgs fields in a way that they come from harmonic maps that are equivariant for Hitchin representations, and we can prescribe their spectrum. So this is a matrix with a dz, and at least locally, around every point, I could, let's say R phi, I could try to diagonalize it. And I'm claiming we can do it in a way where you could prescribe these eigenvalues. The eigenvalues are really holomorphic one forms. Okay. So now, if you kind of think about all the geometry I said, so this here, this is tangent space to a flat in Xn. So the basic example of a flat in my space Xn is diagonal matrices, and this is the tangent space. So if HR lands in a flat, or lands in, this flat, that means that AR is equal to the identity, and the derivative of HR, up to identifications, is really R times the derivative of the map F. So that's the point of prescribing the spectrum. I could say, if it's inside a flat, then I know what harmonic map it should be. And then from my picture that I drew before, we should think it might be close to a flat, and there are estimates to the Takuro-Mochizuki, all about Higgs bundles proven in 2016, that we transformed into this framework that show that away from points where phi I is equal to phi j, or I not equal to j, we have, in some precise sense, the derivative here is actually close to the derivative of f. So the sort of, whatever analysis assumes these Higgs bundles does confirm these pictures that we drew. And the significance of this condition is you really have to think about the sort of symmetric space, but yeah, if they're all distinct, then you can put yourself tangent to a unique flat in the symmetric space, and if they match up at a point, you're tangent to many flats. So this is where something very hyperbolic could happen and you transition. And then, once we have our map that looks like the Schwartz P surface most of the time, we found a way using gauge theory, plus something called the log cutoff trick from minimal surfaces, to prove that for R large, HR is unstable. Yeah. Any questions? Mm-hmm.
the cutoff trick doesn't work in all the dimensions, right? That's why it's quite different.
Yeah, so what we actually do is we take a variation of a minimal surface in the Euclidean space, and then we use the log cutoff trick on that.
Okay.
And then we find some way to transport that to a variation in the symmetric space.
Yeah, thanks.
Okay, so that's the main thing I wanted to present. I'll just state some other results and directions very, very briefly. Firstly, I want to mention there's lots of work on a simpler space, for which we know a lot more than this space Xn, which is the product of n copies of hyperbolic space. And I should have mentioned this earlier, but there was prior work done by Markovich, myself, and Peter. In 2022 that really greatly influenced our work here. That was we studied the simpler space, and that's how we got a lot of ideas. I think this is a really awesome thing to study because it's much more hands-on, and you can use tools from like classical hyperbolic geometry and quasi-conformal maps to study it. And we also, along with it, we studied products of R trees, that I guess touches metric spaces. Yeah, and I really like this subject. Whenever I have a question about Xn, I usually ask first for h2 to the n. So I keep working on this topic. Yeah. And the last thing I'll present is a theorem with the same co-author, extremely vaguely stated. I say 2025, posted on my webpage in 2023, got lazy, posted on the archive 2 weeks ago. But so, I don't know if it's new. Take array, R going to R5, giving these harmonic maps HR, Xn, or any other symmetric space. I draw this picture that I drew before. And just the statement is, so phi is not nilpotent, so it's a matrix with a dz. If it's not a nilpotent matrix, then this picture is totally true. The previous work in this direction can kind of show it in some more particular cases that we were able to apply to prove the theorem. So high energy harmonic maps or large area minimal surfaces really do look like this in symmetric spaces. And we also have sort of precise rates of convergence. And maybe within the metric space theme, what I've really been drawing here is a portion of a building. So a building, I won't define it, but you can think of a bunch of copies of Euclidean spaces glued along hyperplanes in some rather symmetric way. And so in some sense, it, let's say, subconverges to a map to a building that we can write totally explicitly away from some finite set. And that finite set is where things transition between different flags. Yeah, and that's the theorems I wanted to present. I'll just put one sort of problem on the board, which is to develop theory of, let's just say, large harmonic maps plus minimal surfaces for cat zero spaces. So I drew a bunch of pictures and argued on those heuristics, and then to prove everything we used this very complicated machinery involving complex analysis. So it'd be interesting to try and make this work in a more general context. Cool, well, thanks.